Have you ever wondered what makes up the majority of our universe? It's a question that has puzzled scientists for decades. In our quest to understand the cosmos, we've stumbled upon a concept that is as intriguing as it is elusive: dark matter. Now, don't let its ominous name fool you. Dark matter is not some cosmic villain. In fact, it's an essential component of our universe, constituting about 85% of its mass. But here's the twist. We can't see it, we can't touch it, and we can't interact with it directly. It's like a ghost in the cosmic machine, present everywhere but almost impossible to detect. This invisible entity, this dark matter, is one of the greatest mysteries in modern science. It's like a puzzle piece that fits perfectly into our understanding of the universe, yet remains hidden from our sight. So, if we can't see or touch it, how do we even know dark matter exists? Scientists didn't just pull the idea of dark matter out of a hat. No, in fact, it was the peculiar behavior of the universe that led them to propose this elusive substance. There are several pieces of evidence that suggest the existence of dark matter, and today we're diving into two of the most significant: gravitational lensing and galaxy rotation curves. Let's start with gravitational lensing. This is a phenomenon where light from a distant source, like a galaxy or a star, is bent around a massive object. Think of it like a giant cosmic magnifying glass. But here's the thing. Sometimes, the amount of light bending we observe is far more than what we would expect, based on the visible mass of the object doing the bending. It's as if there's an invisible mass contributing to the lensing effect. This invisible mass, scientists propose, is dark matter. Now let's turn to galaxy rotation curves. Usually objects closer to the center of a galaxy should move faster than those at the edge, much like how planets in our solar system orbit. But when scientists measured the speeds of stars at different distances from the center of galaxies, they found that stars far from the center were moving just as fast as those near the center. This shouldn't be possible based on the visible mass alone. The only way to explain this is if there is a significant amount of unseen mass, aka dark matter, influencing the galaxy's rotation. These are just two of the ways that scientists have gathered evidence for dark matter. And while they can't directly observe dark matter, they can see its effects, like a puppet master pulling the strings behind a curtain. The universe is behaving in ways that can't be explained by the matter we can see, and this invisible yet influential player, dark matter, seems to be the prime suspect. It seems that even though we can't see dark matter, its influence is everywhere. The question now is, how do we find something we can't see? It's like trying to catch a ghost, isn't it? But fear not, scientists are not ghostbusters. They're equipped with cutting-edge technologies and methods to unveil the secrets of the universe, including dark matter. Now let's dive into some of these intriguing methodologies. To begin with, we have deep underground detectors. Picture a space far beneath the surface of the Earth where cosmic rays can't interfere. Here, scientists set up extraordinarily sensitive detectors, waiting patiently for the elusive dark matter particles to pass through and leave a trace. It's kind of like setting a trap for a mystical creature, hoping it will eventually show up. One of these underground detectors is the Large Underground Xenon Experiment, or LUX for short. Buried 1 mile under the Black Hills of South Dakota, LUX is on a mission to detect weakly interacting massive particles, or WIMPs, a leading candidate for dark matter. But that's not all. We're also scanning the skies with powerful telescopes. We're using these cosmic binoculars to observe phenomena like gravitational lensing, where the path of light from distant galaxies is bent by the gravitational pull of dark matter. This distortion gives us clues about the distribution and amount of dark matter in the universe. And then there's the Alpha Magnetic Spectrometer, or AMS, aboard the International Space Station. AMS is designed to study cosmic rays, searching for unusual patterns that could hint at the presence of dark matter. So you see, the search for dark matter is not a shot in the dark. It's a strategic and calculated pursuit, leveraging the best of our technological advancements and scientific understanding. The hunt for dark matter is a challenging yet exciting journey, taking us to the edge of our understanding of the universe. Imagine that, standing on the brink of a new frontier, poised to uncover the secrets of the cosmos. Isn't that a thrilling thought? So, what could this elusive dark matter be? It's a question that's been stumping scientists for years, and while we don't have a definitive answer yet, we do have some intriguing theories. One of the leading theories involves something called WIMPs, or weakly interacting massive particles. Now don't let the name fool you. While they might be weakly interacting, they're far from wimpy. These particles are thought to be incredibly heavy, up to 100 times the mass of a proton. but they're also incredibly elusive. Because they interact so weakly with regular matter, they're incredibly difficult to detect. Imagine trying to hear a whisper in a hurricane. That's the challenge scientists face when trying to find WIMPs. But WIMPs aren't the only game in town. There's another theory that suggests dark matter could be made up of machos, or massive compact halo objects. These aren't particles like WIMPs. Instead, they're objects like black holes or neutron stars, objects that are very dense but don't emit any light. They're called halo objects because the theory suggests they could be scattered in a halo-like formation around galaxies. These are just two of the theories floating around the scientific community. There's also the idea that dark matter could be made up of axions, hypothetical particles that are incredibly light and interact weakly with other matter. Or it could be that dark matter is made up of something entirely different, something we haven't even thought of yet. These theories might seem far-fetched, but remember, it's through these imaginative leaps that science progresses. After all, it was once thought ridiculous to suggest the Earth revolved around the Sun, and while we may not have a definitive answer to the dark matter mystery yet, each theory brings us one step closer to understanding the universe around us. While we don't have a definitive answer yet, each theory takes us a step closer to solving the mystery of dark matter. What does the future hold for our understanding of dark matter? As we venture deeper into the realm of the unknown, our aspirations grow as well. We're not simply content knowing that dark matter exists. We want to understand it, to harness it, to make it less of a mystery. In the future of dark matter research, we can expect to see fascinating breakthroughs and advancements. This is an era where we're not just peeking through the keyhole of the universe, but pushing the door ajar. Scientists are already developing more sensitive and precise detectors, which could provide the much-awaited confirmation of dark matter particles. The next generation of space telescopes, like the upcoming Euclid mission by the European Space Agency, is expected to probe the dark universe like never before. These telescopes will map the distribution of dark matter across the cosmos, revealing its influence on the formation of galaxies and clusters of galaxies. Moreover, advancements in quantum computing and artificial intelligence could revolutionize our approach to dark matter research. These technologies could help us analyze astronomical data at unprecedented scales, potentially unveiling subtle clues about the nature of dark matter. Furthermore, the unification of quantum mechanics and gravity, one of the holy grails of theoretical physics, could provide a radical new perspective on dark matter. If we can successfully marry these two theories, we might be able to understand why dark matter interacts so weakly with ordinary matter, or even predict new types of dark matter yet to be discovered. But let's remember, science is a journey, not a destination. Each answer we find often raises more questions, and that's the beauty of it. As we push the boundaries of our knowledge, we become more aware of the vastness and complexity of the universe, making us humble seekers in the grand cosmic theater. As we continue to seek answers, one thing is clear. The universe has many more secrets to reveal. And as we unlock these secrets, we're not just learning about the universe, we're learning about ourselves. Dark matter, a mystery that continues to baffle and fascinate us. As we journey back through our exploration today, we've peeled back the layers of this enigma. We've marveled at the importance of dark matter, understanding how its unseen presence shapes the universe. We've examined the compelling evidence for its existence, from the rotation of galaxies to gravitational lensing. We've also ventured into the ongoing search for dark matter, a quest that pushes the boundaries of our knowledge and technology. We've delved into the theories that seek to explain this elusive substance, from WIMPs to axions, each more intriguing than the last. And we've peered into the future of dark matter research, a future filled with tantalizing possibilities and incredible potential for discovery. As we wrap up, let's remember that our journey through the cosmos is far from over. As we delve deeper into the cosmos, who knows what other mysteries we'll uncover next?